All right, let's dive into a really fun, classic geometric puzzle. The question is, how do you perfectly fit a square inside of any triangle? Now, it sounds simple enough on the surface, but as you're about to see, trying to solve it directly, well, that can be a real head-scratcher. So here's the challenge. You've got a triangle, any old triangle. And your job is to draw a square inside it so that one side sits perfectly on the base and the other two corners just kiss the other two sides. I mean, sketching it out is easy, but how do you construct it with perfect precision? And yeah, that's the big question, isn't it? Where do you even start? If you just try to guess, you'll find out pretty fast it's almost impossible. How long should the side of the square be? Where on the base do you even start drawing? A random guess is pretty much guaranteed to be wrong. You know, when you hit a wall like this, the best problem solvers don't just keep banging their heads against it. They look for a different way in. This is a brilliant strategy made famous by the mathematician George Polya. If you can't solve the problem you've got, try solving an easier one first. So let's try what's called relaxing the constraints. The really hard part is getting all four corners of the square to land perfectly. So what if we make it easier? Let's just aim for 3 corners to be in the right spot. 2 on the base and 1 on a side. And that 4th corner, for now, we'll just let it land wherever it happens to land. Okay, so here's our first try. We've drawn a nice little square. You can see 2 of its corners are right on the base, and the top left one is perfectly touching the side of the triangle. But look at that top right corner. It's just floating there in the middle of nowhere. So this obviously isn't our final answer, but believe it or not, this is a super important first step. So one of these imperfect squares doesn't really tell us much by itself. But what happens if we try again? What if we draw a slightly bigger one, following the same simple rules? Do we start to see any kind of connection here? So we draw another one, and another one, and another. Each one is what we can call a helper square. They all follow our new, easier rules, but none of them is the perfect solution. Now, this might look like a bunch of failed attempts, but what we're actually doing is collecting clues. Now, I want you to focus your attention on just one spot, that free corner, the one that we let land wherever it wanted. Look at where it ends up in each one of our helper squares. Do you see it? Something really interesting is happening. Its path isn't random at all. And this is it. This is the breakthrough moment. All of those free corners from all of our different helper squares, they actually line up perfectly. They form a dead straight line. It's like there was this hidden path there the entire time, just waiting for us to find it. Seriously, this line is everything, because now we know something crucial. The 4th corner of our final perfect square has to be somewhere on this line. We've completely removed all the guesswork from the problem and replaced it with a clear, predictable path. And because we found that line, the actual construction becomes almost ridiculously simple. Let me walk you through it. Step 1. Just draw a line from the top vertex of the triangle right through the free corner of any one of your helper squares. Step 2. Keep that line going until it hits the other side of the triangle. And step 3, that exact point of intersection, boom! That's it. That is precisely where the corner of our final perfect square needs to go. And once you have that one magic point, the rest is a piece of cake. You just drop a line straight down to the base and draw the rest of your square. And look at that, it fits absolutely perfectly. It's such an elegant solution, and we didn't find it by attacking the problem head-on, but by sort of sneaking up on it from the side. Okay, so it works, it totally works, it's beautiful. But if you're like me, there's another question popping into your head right about now. Why does it work? Why do those points form a perfect straight line and not some kind of weird curve? Well, the beauty of geometry is that there's always a reason. And the secret here is a concept called similar triangles. If you look closely, you'll notice that each of our helper squares creates a little triangle with the top vertex. As the squares get bigger, that little triangle they form just gets bigger right along with it. So here's the logic, without getting into a complicated mathematical proof. Think of the top vertex of the big triangle like a projector. Each of our helper squares is just a scaled-up version of the others. As you move the screen further from a projector, the image gets bigger, but every point in that image travels away from the lens in a straight line, right? That is exactly what's happening with our free corner. It has no choice but to move along a perfectly straight line. This amazing technique we just used actually has a name. It's called problem solving by relaxation. It's a super powerful idea. When a problem is just too difficult, you relax or remove one of the tough conditions. Then you solve that new, easier version, and you look for a pattern. And so often, that pattern gives you the exact key you need to solve the original hard problem. And that brings us full circle, right back to George Polya. The big takeaway here isn't just some clever trick for a geometry puzzle. It's a huge lesson in how to think creatively. When you're stuck, don't just push harder. Take a step back. Try to solve an easier version of the problem. Because sometimes the answer you're looking for isn't at the end of that obvious, difficult path, but it's hidden in the beautiful, simple pattern you find by taking a detour. It makes you wonder, right? What hard problem in your own life could you solve by relaxing just one little constraint?